missing on the property after the next day.
Oh man. All right. Well, we have one unresolved thing from last time for me to hit, but do you guys have any questions before I jump in?
I do.
Okay. What?
So, the light, or the spectrum, identifying elements on the spectrum. I don't remember what those lines are called.
They can be emission or absorption lines. Yeah.
So, they discovered that several hundred years ago.
Yeah. A couple hundred, yeah.
Are we still identifying, are we still using that to identify elements on different planets, or have we?
Absolutely. Nope, absolutely. That is prime tool. Yeah, and we've refined it. I mean, we've got computer algorithms to help us now.
Right.
We have spectral lines change with the ionization state of materials. You have molecular emission and absorption lines. So we have found, molecules of alcohol, oh boy, water, carbon dioxide, carbon monoxide, things like that out in interstellar space. So now it can be molecules. We can also identify the strength of magnetic fields from broadening and alterations of the lines. So we can look at materials around strong magnetic sources like magnetars and things like that. So, yep, we're still refining and figuring out even more information we can squeeze out of the light.
Sure, makes sense.
Yeah, but it's chemistry across the entire universe.
So they're
absolutely.
Taking it from a static observation, meaning they take photographs or whatever, to something that's more live or more dynamic, I guess.
Yeah, we use now diffraction gratings more than a prism, and you can get really expensive, very high quality diffraction gratings, and then we use CCDs to digitize it immediately. So the light falls directly on a CCD camera like it would any other imagery we do now, and then the computer can work to identify all that stuff rather than humans having to figure things out and measure the distances by hand on some photographic plate like they used to. But yeah.
You said the ionization of, they can see the ionization of things.
Right, it just gives you different lines, yeah, or alterations of lines, yeah.
Over time, to watch that.
If that's changing, yeah, yeah, yep.
Interesting. I like it.
How are they going to find instances or the possibility of alien life on other planets through looking at spectral lines?
One of the things we would look for, and it wouldn't be, any one measurement would probably not be a guarantee, but if you had a convergence of multiple lines of evidence, you would then say, hey, I think we've got something. That would be chemistry that's not in equilibrium. So like oxygen in the atmosphere here is not in equilibrium. If you used Agent Orange and killed everything green on the Earth today, which would be a bad thing, you'd have about,
We're on our way.
We're on our way, that's true. Right, but you'd probably have 2-3 weeks, I think, before people on Earth, like the elderly or children, or people with respiratory distress already would start to die. Within a month, healthy people would start to run out of oxygen and die. Sherpas who lived in the Himalayas and came down to sea level may make it a month and a half or something like that, but eventually the oxygen would be gone. It would be absorbed into the mineralization of the crust, which is ongoing. When the, let's see, get the word, cyanobacteria came about and oxygen started being produced, you had a tremendous oxidation of the Earth's crust then, and you have the red beds like red earth in Oklahoma and the Sedona red rock and like that. That's all early iron mineralization from oxygen. But eventually the oxygen kept being produced by life and pumping it up. So you would look at a distant planet, you look at an excess of oxygen. But we see disequalized, is that the right word? Or chemistry that's not in equilibrium, thank you. Like on Titan and on Saturn, you have methane that is being pumped up. And there is thinking that maybe that is some form of life that's driving that chemistry there. Or maybe not, maybe it's a natural process. We see methane in spectra on Mars. And it's a possibility methane would be produced by bacteria or something similar to that in the crust, protected from UV light, protected from the harsh chemical environment of the surface of Mars, and tucked down in there where there's water and there's warmth and there's a trickle of carbon dioxide coming down like that. So we don't know. There's a natural explanation for that as well. So you would just need multiple lines to figure that out. So that's what we would do. We would look to see what the atmospheres these distant exoplanets are made of.
Yeah.
So
I think they just launched a test satellite.
yeah, TESS.
Yeah,
Yep.
to look for variabilities in exoplanets to determine if there might be life on them.
Yep, it's pretty exciting. It is. Yeah. We're in an amazing age right now with the acceleration of discovery and aided by the acceleration in the quality of instruments we can make and the computing power and that we have to sift through now terabytes of data without too much stress.
So is there any one discovery, one event that prompted or started this discovery phase we're going through?
No, I think it's largely following Moore's law, our ability to build upon the previous improvements technologically and just keep leapfrogging upward. The ability to model the stresses. I mean, like the James Webb last night. What a miracle of technology. I mean, the computers did all the modeling for how much material they could take out of those beryllium mirrors, with each little vein being a slight different width. And you couldn't have done that by hand for anything. But you got the ability to model that, calculate the stresses at all those junctions. Is a highly nonlinear problem. And so that was made possible by computing power and software development and like that.
Or maybe it's just our simulation overlord.
Yeah, okay.
A couple of tidbits.
There's that too. So, all right, so any other thoughts? Any other questions? So today we're largely going through we've gone through the details of the sun, and so it's our closest star, so it's one we can study the most easily, and we can now generalize out across the galaxy and across the universe. But we just had this one lingering thing. Sometimes my brain doesn't engage up here, but we're looking at measuring distances, and then we looked at the Hipparchus and then the Gaia satellites, and that their precision is going to be these incredible amounts. 0.00002 arc seconds at 15th magnitude, 0.002 at 20th, to create a map of 1 billion stars. We have possibly up to 1 trillion or 100 billion stars in our galaxy estimated. So that's about 1% of the low end number. And someone pointed out that if the distance here is 1 over p and the angle in arc seconds, then that would be much more distant than the entire galaxy. Well, I just didn't connect while standing up here was that this isn't the distance arc second, it's not the variation, it's the error in the measurement that is what this precision is is expressing. So we're going out that far, but we're going to know the answer for the distance of objects in the nearest 1% to that level of precision. So that, it's a difference between, this isn't the measurement we're actually making of the motion of the star as the Earth goes around the sun. This is the precision in the measurement we make when we do measure it. And so those are two different numbers. And I got this from the Gaia catalog saying, in the early 2020s, objects 3 to 13 magnitude of positions measured to 5 micro arc seconds. Parallaxes to 6.7 micro arc seconds, proper motions to 3.5 micro arc seconds per year. For the faintest stars, the equivalent numbers will be several hundred micro arc seconds. So
micro arc seconds is 10,000 of it?
Yeah.
Okay. And so could you refresh my memory what P is?
P is the angle that you measure. The angle of motion caused by the Earth going around. So it's the... Right, it's the, put your finger out and switch eyes and you see your finger hop back and forth. That's P.
Right.
Yeah.
And PC is parsec. Or parsec.
Yeah, parsec, yep. That's just units, yeah. So units of parsecs, units of angle, yeah. So that was good. That was, sometimes my brain just doesn't catch up with what I need to be doing, so. We talked about absolute, I think we've covered this, but I'll just kind of brush through quickly to get back up. So we talked about the need to come up with a standard distance so we can compare the brightness of everything sort of easily. And arbitrarily we decided that 10 parsecs would be our standard distance. So just like standing up on a hillside and looking out from here towards Denver, you see street lights going off in the distance. But the ones real close or bright kind of make you squint a little bit. The ones at the distance are tiny little points, but you know that all the salmon colored streetlights probably have the exact same wattage, same Cobra head light bulb lamp and all, and they're all the same actual brightness. So it's just because they are far and near that you get an apparent brightness difference. So apparent is nice, but once you know the absolute magnitude, what they would be if you took them all and put them 10 miles away in my streetlight example, or 10 parsecs away for stars and anything else that is giving off light, then you have a really quick way to compare the actual energy output of things and like that. And you can get the, so the absolute magnitude is the apparent magnitude minus the absolute magnitude with this little log 10 equation here with the distance in parsecs. So you solve for distance in parsecs if you know these two differences, or you can figure out the differences. If you know its distance, you can take how bright it looks and you can solve for the absolute magnitude. Yeah. From that we can get luminosity, and we find a really nice relationship where the luminosity of something divided by the luminosity of the sun is the same as the square of its radius divided by the radius of the sun times the temperature divided by the temperature of the sun squared. So very straightforward equations again based on radiation laws, and we get to put together these, go over this one here, fantastically simple charts showing all the bulk of the stars that are out there, going from M up to O classification, hotter and hotter and hotter as you go, so more luminous as you go. Cooler is red, our sun is sort of middle in temperature, low middle, and then up to the blue-white big ones that are pumping out a lot of energy. And similarly, they have lifetimes based on their luminosity, not their size. These are tiny little guys with a very little fuel, but they're not consuming very much hydrogen to make helium and releasing energy, so they can last 1 trillion years. You go up here and it's a million, 100,000, yeah, a million years for the hottest, biggest stars don't last long at all.
So does that mean that the little small guys don't have the hydrogen?
They do. They just don't burn very much of it.
Not burning it off?
Nope. As we'll see in a little bit as well, they're almost entirely convective. So hydrogen from, if this is a star right here, this big circle what we use for the Lakota stars, that's the star. There's convective circulation going almost all the way through and down to the core. So it can bring in a larger percent of its hydrogen to fuse over time, where up here, the pressures are so great that almost the entire star is packed solid. It's radiative only. Once stars die, they then swell up and migrate off. In our chart here, they move as they age, becoming cooler, but much larger and more luminous. So. And we can, by looking at binary stars, which two out of every 3 stars are multiple star systems on average, we can weigh these stars, going right back to Kepler. And so we can see the mass of the 2 stars added together equal their separation in astronomical units divided by their period in Earth years. So we can go right back to Kepler and use Earth numbers to weigh stars. And this all came initially from figuring out their temperature, figuring out what they're made of, getting their spectral classification, and back to light. So.
And the cube, that A cubed is, deals with the spherical nature of the body that they're measuring?
Yeah, I'm trying to think if it has to do with the equation of an ellipse as well, but that's not coming to me right now. Yeah.
What is the purpose of weighing stars?
You know what? How much mass is in there? Yeah. So as we'll see, we can predict the fate of a star in part by its mass.
So bigger the star, bigger the mass, quicker.
The shorter the life.
Shorter the life.
Yeah, and the more violent the death. Yeah. The little teeny M-class stars, as we'll see, just kind of peter out, shrink down, cool off. The biggest stars become the giant supernovas that light up the universe briefly. So.
And knowing this helps answer other questions.
Mm-hmm. Where all the materials come from. Yep. Yeah, we'll get into interstellar medium in just a minute. Yep. Good questions. So we talked about exoplanets before and seeing planets transiting other stars. We see them going across the face of the star. Of course, if you have multiple star systems, a fraction of those are going to be oriented such that the partner star goes in front of the other larger or more luminous star. Rarely will they be exactly the same, but they can be. Anything's possible, any combination. But if they're edge-on, then you can make really good timing and measurement of the size of this and size of this by the light curve that you get. So here's a little star, big star. When the little star comes around the front, it makes a little decrease in the system brightness, and then it comes around, you got both stars side by side. Both stars gives you the maximum brightness. When it goes behind the big star, it's a little bright white thing. You see a bigger dip because that star is entirely gone. So here you have star plus big star minus what the little bit that the brighter small star is taking away. Here you're losing the entire second star and only having the other star behind, so you get a bigger dip right there. So you can figure out radii and luminosity and the separate spectra of the 2 stars as these eclipses occur.
And do they use that information as a baseline to measure the luminosity of other stars?
Oh, absolutely.
Stars?
Yep, exactly.
So this is where they got that information from.
Yep. So the universe gives us all these little laboratory examples. And the more we see, the more we build up a catalog of what's out there. And then we see stuff that is in a either alone, like you said, or in an unusual configuration. We can feather out what's going on better because we have all these things that do happen. Yep. It's a lot of sleuthing for the last century. So here's an example of two stars are more equal in size. One's more luminous than the other, a little bit larger. So you can see the different light curve you get there. It's so outshining its partner that when it's in front, it's still the star of the show, largely.
So in that illustration, the white star is appears to be orbiting around.
Yeah, that's all.
So is that a density thing?
It would be a density thing, yeah. Yeah, I think that's just a sloppy illustration. Yeah. So by looking at tons and tons of stars, we have figured out there's a pretty nice little relationship between the luminosity and the mass raised to the 3.5 power. So now when we look at the spectrum of a star, we know its luminosity. Once you know the luminosity, even if a star sitting all by itself, you instantly know its mass. It's great. And these are not 15-page long equations. The universe is kind of simple in a lot of these relationships, which, as Brian Greene has philosophically stated, like, why should the universe be so understandable? But it is. We can quantify so many things. So similar to solar systems where grains of sand and specks of dust are much easier to make than Jupiter's, because you don't have to have that much stuff to make a little baseball-sized rock. You're going to get a lot more of the small stuff than you get the big stuff, and we see the same thing with stars, that the M-class stars far outnumber everybody else. As you go up in spectral classification, you get fewer and fewer of the stars, but their luminosity goes up so great that these guys up here far outshine all these. So when you're looking at a distant galaxy, you're largely seeing the stars that are up here. You're not really getting a good picture of what's there. You're certainly not seeing planets and dust, and you're not seeing the M and K class stars, but you're seeing these guys. And there really is a strong analogy between, the superstars here and Hollywood stars. I mean, there are just a few people who are Hollywood stars, but everybody on the planet knows what they're doing, and there's news about them, and there's Wikipedia pages about them, and everything like that, versus the average person in the population who just out there, not super visible, but there's a lot more of the average people, so like me. So,
that's why YouTube is so.
Yeah, YouTube is kind of like a telescope that lifts these folks out of obscurity.
So when you say we're only seeing the really bright ones, so you're talking about naked eye?
Naked eye or observationally, yeah.
Our hobby telescopes, but the deep field telescopes can see.
Yeah, but you got to work at it. Yeah, you've got to do something to block these out, or try to figure out what's going on between these super bright pools of stars, because they outshine.
Now, is this a known thing?
Oh yeah, because we can, as we'll see, we can weigh galaxies too. And the bright stars would not give us enough mass by even a minuscule fraction to explain the mass of a galaxy and its mutual gravitation and like that. And even then, when you do figure out how much is going on, and which we can see these guys nearby too. We can sample the nearby galaxy to start to get a hold of this. But we find that there's not even enough to explain that. So dark matter then comes in, and we'll talk about dark matter in the months to come.
So brown dwarfs are
They would be
suns that are not even visible.
bigger than Jupiter, and I believe large enough for some nuclear fusion to occur in the core. So they give off more energy than they get from their surroundings. But yeah, they're
So they're considered stars that never ignited, really. Never really.
not fully, yeah. Yeah, they're They're not acting star-like. If you went up to one, it would look like a Jupiter. It would have atmospheric circulation patterns and stuff like that. Yeah.
So does that mean their potential is just super high? Their energy potential? I mean, do you have to be careful around it?
Yeah, they probably have tremendous magnetic fields and probably are very hazardous environments for people to be around. But almost the entire universe is hazardous to us. We're made to be in this little skin of atmosphere right over the Earth, and every place else wants to kill us. But I do have an article in, I think it was Sky and Telescope or something, from the late 80s where someone wrote an argument why brown dwarfs probably don't exist. Well, no, we found a bunch of them, and it doesn't make sense because it's much easier to make a brown dwarf because it takes less matter than it does to make an M-class star even. So it should keep on going up, and then the number of Jupiter planets should be even higher, and the number of Earth-sized planets even higher than that. I mean, it should just go right on up in number because it's just easier to make those. You would have to invoke some thermodynamic reason that they don't form. You would then have a dip for some physical reason, but I haven't seen that. I haven't seen that come along. So here's about where we ended last time. We talked about stellar populations, the numbering of populations of stars. This is just classifications. We make groupings in our brain. It helps us organize stuff. It's more of a continuum, of course. But I think the numbers should be backwards. The hypothetical first stars that we really, I don't think, have seen much of a hint of yet are the things that the James Webb Space Telescope should pull out. These would be all hydrogen and helium, maybe even some dark matter. It's kind of hard to figure that out, but it's possible. Population 2 stars are metal poor. Now, metal is anything beyond hydrogen and helium. So it's all the rest of the heavier elements. So maybe one generation of stars has occurred, blown up, spewed heavier stuff out that got incorporated into the formation of population 2 stars. They're out in the outskirts of our galaxy. And population 1 stars are, I didn't fix that, did I? Metal rich. I just kind of I need a piece of paper here and make note of the things I need to correct because I never remember later. And these are common in the spiral arms. So materials are being recycled and created and brought back in and reincorporated into the next generation of stars. And when you have the largest stars, 1 million years, 10 million years, that's pretty quick cycling of making stars. And when we get to the next section of material, we talk about galaxy and galaxy formation. The spiral arms that you see are, again, illuminated by these big, bright, short-lived stars. And they are the leading edge of density waves traveling around in the interstellar medium of the galaxy that isn't really more dense there. It's just this shock wave is traveling around, shockwave-like thing or wave. And it's kicking off star formation of these big, short-lived, bright stars. So it's like a gust of wind blowing embers ahead of it over a fire, something like that. I'm trying to come up with an analogy real quick. But they look more substantial and different than the rest of the galaxy than they really are. It's just these super bright O and B type stars that are hogging the stage. So let's talk about this interstellar medium. We do see great lanes of gas and dust between the stars. This is the interstellar medium. Just like the early universe, it's about 75% hydrogen, 25% helium. You've got a little carbon, nitrogen, oxygen, calcium, sodium. As I said before, alcohol, water, formaldehyde has been detected between the stars, all looking at the spectral absorption of this stuff. And there's dust, actual grains of material that have started to stick together that makes up these darker nebula. So we have two main classifications of nebula. If it's largely gas and some dust, and it's being illuminated by high energy stars. They're pumping out a lot of ultraviolet light that pumps the electrons up in the gases, and they emit, so the gases glow. You have an emission nebula. If the light is just bouncing off of dust, you have reflection nebula. And you can tell the difference in the spectra once you look at it, what the two are. If the light is passing through the gas and dust, then the light is either scattered away or absorbed and converted into heat or something like that, and we don't see it except for things like the James Webb Space Telescope will help us seeing things that are warm in the universe. Just like the sunset going through the atmosphere and the gases and dust that make up our atmosphere, the blue light is preferentially scattered out and the red light makes it through. So more distant stellar light sources are reddened. They are artificially reddened by that. But it's a different kind of reddening than the reddening caused by velocity. So you can tell the difference between a redshift reddening, we talked about redshift last month, where the light wave is elongated because of the motion of the object away from you, and the reddening created by the subtraction of the blue end of the light coming to you. So everything in the universe has a temperature. Like she said last night, the background cosmic microwave background radiation temperature of the left over from the Big Bang is 2.5 degrees roughly Kelvin. And wherever there are stars and things, you have a little extra energy warming things up. So gas clouds and clouds of dust and like that are receiving photons from nearby stellar sources and warming up a few degrees. And when you have warmth, you have motion of molecules, and that's passed to the grains of dust, and they pass it back to the gas. And so you have this little extra kinetic energy in the gas cloud that kind of holds it up. It's a very weak version of what's going inside of stars themselves. Still, go out to a gas cloud or dust cloud in deep space, it's going to be one of the best vacuums you've ever seen on Earth. It is really close to a vacuum, but there's more stuff there per cubic meter, cubic light year than there is away from that or between the galaxies. And what we believe is something starts a collapse. You've got to disturb this thermal equilibrium that the gas clouds are in. So maybe a star blows up, you've got a shock wave coming along, it passes through, and you start to get a collapse, you get random fractioning up, oh, that's not the right word. I don't know what the word is, though. Fragmenting, there you go, thank you. Fragmenting of the gas cloud and the material, and local areas start to get a sense of down. You have a little more density in a spot, so now there's a preferential direction for things to start to fall together, and so in there you start to get stars. First to come on and the first to die are the big ones, but eventually stars of all sizes forming in there. When a gas cloud starts to fall together and create stars, you can get 10 to maybe thousands of stars forming. We see star clusters all around the galaxy. Many of these are Messier objects pictured in posters like that, or Caldwell objects, things that we like to look at in our backyard telescopes. Get these little roughly spherical or patchy conglomerations of lots and lots of stars that fit inside of an eyepiece. And here you have what are called Bach globules. These are believed to be gas clouds still falling together, still trying to create stars, while their maybe more massive cousins have already gotten their act together and have ignited and blown away the material. Unused stuff goes back into the average medium in between the stars. So our model is we start with the gas cloud that begins to collapse. This is a rehash of how solar systems formed, but we're dealing with stars now, so it can't hurt to hit things twice. But it is ridiculously unlikely that any gas cloud or dust cloud out in space won't have some net rotation in some direction. For it to be completely stationary compared to everything else around it is just not so improbable that once it starts to collapse, something starts to win. Some preferential direction starts to manifest. You start getting a rotation around an axis, and then the collapse occurs downward onto a disk. In the center, the star itself comes together. As it heats up, it repels material that's infalling, but yet gravity is becoming stronger too, pulling material in. So you have this little tug of war. Some of the energy or angular momentum is lost out through jets, we believe. And you got this supply of material versus the traffic jam in the middle that works itself out to some final star size. And this takes a long time to happen. You got from gas cloud to dust disk. This star in the middle is slow. It's very, very cold. Then it starts warming up. So it's approaching our temperature scale of main sequence stars. It's also slowly becoming more luminous. So it starts to give off infrared, then maybe visible light, and then comes on to the main sequence to spend most of its life. So you can chart it, you just have to go way off the graph on the HR diagram to see that. So again, like Hollywood stars, the big bright stars often don't live very long. I don't know, they seem to have short tragic lives, and we just lost a musician that was on the news this morning in a hotel room at like 28 or something, but really, really successful, influential person. The very dim stars take a long time to come on as well, 150 million years to go from gas cloud into their stable main sequence life, where these big monsters, 60,000 years, they're ready to get going. I mean, gravity is so dominant, so fast, that it just pulls everything together and gets the star going. Our sun probably took about 50 million years before it began its roughly 10 billion year lifespan on the main sequence.
And they're all made out of the same stuff.
All made out of the same stuff.
So the only difference is the
Matt.
amount of materials
And
gravity that affects them.
Yeah. Well, right. The amount of materials is all, yeah, because the more material, the more gravity. Yeah. All comes to mass. Mass determines the main features here of temperature, luminosity, lifespan, time to come on, and what's going to happen to them when they die. Yeah. So figuring out the mass of stars was a really big deal. Having binary stars allow us to decode the actual masses of stars. We know our star, we know its temperature and its radius really well. We can look at the planets going around it, see how long it takes them to go at what distance, and figure out the mass of the sun using Kepler again. So we had one data point, and then when we had binary stars near and far, we were able to paint the rest of the picture. Yeah.
So, color seems to be shifting on this. Generally, you think of blue as cold and red as hot.
Yeah. I think that comes from the refrigeration industry. Because were you here last time for Wien's Law? Oh yes, we were. Okay. If I can go back. Do you mind if I just zip through a whole bunch of slides back? Because it's an important concept to cover. I'll go back to Wien.
I missed the first 20 minutes last time.
Okay. Blackbody radiation. Here we go. So we have the spectrum going from radio way down here up to infrared, and then up to visible from red to blue, and then ultraviolet, and then up to X-ray and gamma ray. And what we know from what are called Blackbody emissions. Do you know where the term blackbody comes from and how we measure this in the laboratory? You create a cavity, just picture maybe a big sphere, and you heat it up to a temperature. And you poke a small hole, small as possible, in one side, and you measure the emission, light emission coming out of that little hole. So the black body is this cavity inside that's coming up to some temperature. So what we found is that as you warm things up, like something that's 5,000 degrees, that little hole that you poke will glow in the red area. So roughly similar to what the burner in your stove is doing, or the oven. When you turn the oven on, you see it glow red. It's coming up into the low end here of visible light emissions. But if you could get the entire oven up to 5,000 Kelvin, then its entire interior would glow with that color. If you warmed it up more, then it would glow with a yellowish center peak spectrum. Glow up further, it's going to become more blue, hot. Get even hotter, it'll primarily give off ultraviolet light. So the very hottest stars give off their peak energy in the ultraviolet. So you have, by temperature, a peak that changes. This lambda max is the wavelength that is the peak at any given temperature of an object. What you also get is the total amount of energy, or the luminosity that we've been using on the HR diagram, is the area under this curve. So you can see on a cooler temperature, there's not as much area. This is calculus. So this is what calculus gives you, is the area under the curve when you have a shape like this. As you heat it up, your temperature goes up, but the overall energy coming off of it increases too, which counts everything from down in the infrared up to ultraviolet. And hotter yet, even greater area underneath the curve.
So you're saying that everything under the curve is being emitted?
Right, everything is, yeah.
But the peak, so...
The peak moves up, yep.
What's being emitted is the lambda.
Yep, so the 5,000 degree stars are yellow-orange here. Cooler, like 2,000 degree stars, are going to peak in the red. So a cool poker here is only giving off infrared. If you have night vision goggles, this thing would be really bright. But as it warms up more and more and more, it starts to give off some red in the visible, and then orange red, and then kind of a white hot. Humans have a peak too. It's down here in the infrared. It is a very squished down, narrow, visible part of the spectrum. And humans glow, and that's why night vision goggles work. Or you can see the bad guy running down the alley with night vision goggles on, or we saw a lot of like Iraqi war bombing stuff from the airplanes with night vision type stuff. And you would see a hot car engine, and you'd see people running around. And yeah, so we find uses for everything in science. So here's humans right over here. So everything gives off some peak radiation. We're at 98.6, is that right? Or 90, roughly. And even the universe itself has a peak energy emission down at 2.5 degrees Kelvin. So, all right.
So theoretically, there are hotter stars than what's on your graph. On the graph up here.
Oh yeah, in fact that last one, I was going to just mention that to you. Sorry to those at home. So here's 15,000 degree Kelvin stars are giving most of their energy off in the ultraviolet. So when you have these emission nebula, and they have big O and B type stars in them, they're being super pumped up with energy that we don't see with our eye at all. but they re-emit it in the visible light. They drop the energy down and re-emit it at whatever their chemical emission lines allow. And we see the star looks kind of bright, but then this nebula behind is glowing with a lot of the energy that we'd be otherwise missing. It's being down converted for us.
So we have absolute zero.
Mm-hmm.
Is there an absolute maximum hotness?
No, I think no, because even in the hottest, largest star, and we'll see that there's a lot of debate as to what the largest possible star is. I think it's like between 180 and 250, or maybe it's in the upper 200 solar masses. I guess beyond that, it would either shove off so much material because the temperatures are so high in the center, but millions of degrees. We can get some of the plasma, even outside of our sun, gets up to millions, maybe even tens of millions degrees, but it's rarefied. So yeah, I think even isolated or near vacuum particles can get accelerated to temperatures that are equivalent to even higher than that. So yeah, I don't think there's there's probably some limit, but I'm not aware of it.
Well, the Big Bang would have been extremely hot.
Yeah, we're going to go into the details of the Big Bang in the future. At the very earliest parts, particles as we deal with them now didn't exist. Yeah. So it's kind of hard to say what a temperature.
Atoms couldn't exist
right.
At a temperature that high.
Yeah, even quarks took a while to cool out. Yeah. Excellent questions. You guys are on fire. Is it back up here?
It's funny that the spectrum, the color wheel spectrum's blue is cool.
Right.
Interesting.
Yeah.
I wonder why.
I think it's physiological. When humans are hot, we get flush, and our blood comes to the surface, and our body's trying to radiate heat. So it's actually raising the temperature of your skin to raise your black body temperature, so you radiate that way faster. When we get cold, the body pulls the blood in to keep the organs in the brain warm, and we get blue lips, and we can see more of the bluer coloration in us. So I think it's it's human-centric.
We should all be warm and fuzzy with this nice blue background.
Absolutely. Yeah. All right, so where were we? That's just speculation on blue and red. I don't know if that's really true.
So it's a color that he's painted on a wall, you feel different too, so it's kind of interesting, maybe it's psychological.
Yeah. Yeah, we have cinnamon is red, candy, but then peppermint we make blue, and we have our own little story going on about what red and blue mean. All right, so T-Tauri stars are an important stage of stellar formation. We're still trying to figure out some of the details here, but we think that once this is what pillars of creation, I believe, is what this is, and you have the point where the stars need to get rid of some of the gas and dust around them. Oh, that's not the next thing. So T-Tauri stars seem to be stars that have just recently turned on and helped fill in the gap here of the formation of stars. And the radiation pressure is enough that it starts to clear out the neighborhood. So planets that are forming better get it now, because the buffet is about to end and the star is turning on and it's shutting off the easy access to gas and dust for further formation. Then we do see examples where we have eroded gas and dust clouds with stars emerging like here and here from the material.
So what do you mean by turning on?
Well, you have some initial point that nuclear fusion starts, in the center of the star, so heat starts to build rapidly. You still have new material falling in, and that's contributing to heating the protostar. But like in our sun, we talked about the walk that it takes for a photon to get out from the center where fusion is occurring out to the photosphere and leap off into the universe. It can be 500,000 years. So smaller stars, less time, bigger stars, more time. Takes a while for that energy to finally get to the surface and start to illuminate the surroundings and heat the surroundings and push gas and dust away. So we still have a solar wind now from our sun turning on that is streaming out through the solar system, creating a heliopause, a bubble of the solar environment out beyond Pluto and out among the Kuiper belt objects like that.
Okay, so then why do you say that, when the stars turn on, the planets better have their act together?
Because that radiation pressure, light has a pressure, and the heating of the material makes it expand as well. So you have expansion and motion away. Everything clears out. Yeah, a cloudy, dusty solar system will rapidly become clear and visible. You can see from planet to planet and see the star in the center, both from inside and from the outside. Yeah. So what's going on in the core of a star? The energy generation is just what we said, is nuclear fusion. We have 4 known forces. Gravity, that's pulling everything together, and when you pull things together, they heat. So that's the initial energy source, is the infalling and compression of material. You have the strong nuclear force, which holds the atomic nuclei together. The weak nuclear force, which is in part responsible for the decay of nuclei, atomic nuclei. And electromagnetism, that's the electron shell. This is chemistry, this is light, and like that. And all these play a role in what's going on inside the center of a star. So again, fission is the breaking apart of heavy atoms. So you start with uranium. It has a lot of protons and a lot of neutrons in there, and you throw a neutron in from an outside source, or you just bring enough uranium together that their random decay will spit a nucleotide out that hits another uranium. And it's just like billiards. It breaks the balls apart, and energy is released. And we can get a tremendous amount of energy, power cities and civilization from little pellets of uranium that way. But that is not very much energy compared to what you get out of fusion. When you get hydrogen and you overcome the repulsion of the protons, they're both positively charged, they don't want to be pushed together, and you make them bind through the strong nuclear force, you get the largest amount of energy out that you can from any nuclear reaction. And this is what powers our sun and all the stars. Just to give you some weird little numbers here. 4 hydrogen nuclei weigh 6.693 times 10 to the minus 23 kilograms. 1 resulting helium nucleus weighs 6.645 times 10 to the 23, that should be a G, kilograms. Typos. The difference is this tiny little bit of mass. That tiny little bit of mass is the photon release. That's the energy, and also neutrinos. But it comes racing out from the reaction. And E equals mc squared shows us that when you plug in that amount of mass, you get that amount of energy in joules. 0.43 times 10 to the minus 11 joules released for each single reaction. And that's actually enough energy to lift a fly 0.001 inches into the air. Just 4 little hydrogen atoms can lift a fly an easily measurable amount.
That's pretty significant.
That's very significant. And in our sun, we're getting 5 million tons converted into energy a second. So that's a lot of fly lifting. And for our sun, that gives us 10 billion years on the original hydrogen supply before other things have to start happening.
Okay, so we've been trying to do fission here.
Yes, and we can do nuclear fission. We can take hydrogen and mash it into helium. Absolutely, we have reactors to do that. That's
Fusion, on the other hand, is a little harder.
yeah, but we do have fusion reactors. Yeah, we do have those.
That's what I was talking about.
Yeah, fusion.
That's what I meant.
Yeah, fusion. But the problem is,
And that's just overcoming the forces of the atom.
yeah, electromagnetic repulsion of, yeah, you
But
got,
yet in the sun or in stars, gravity overcomes that.
correct. That's the problem.
But yet,
You're trying to do it,
overcome our gravity, no problem.
yeah, we're trying to do that in the laboratory, in the reactor. And so we have to use magnetic bottles or configurations of powerful magnetic fields to force the hydrogen together to the point that it creates helium and releases energy. And what we haven't been able to do is to get more energy out than it takes to do that in 1 atmosphere pressure sitting on the surface of the Earth. So we can do it. We've certainly done it. We've many times, and there are probably active, fully functional fusion reactors on the Earth. They're just not over unity. So they cost more to run than they give you back, and that's...
So it's just been easier to do fission.
Right, fission, you don't have to have the same pressures. Yeah, all you have to do is bring uranium together close enough and pure enough, and it just does it by itself. I think in Africa we have evidence of a natural nuclear fission reactor. It just, the way the crust formed and volcanism and whatever processes occurred, you had enough uranium in a pocket in the Earth that fission occurred in the past. We have fission byproducts in highly radioactive soil and like that. It's all natural. So yeah, fission can happen without anybody.
They just made a movie about that.
Oh, did they?
Black Panther.
Yes, I think so. Thank you very much. Yeah, that's what's powering me.
So I'm still confused, because gravity is an insanely weak force.
Mm-hmm.
Yet, it's an insanely strong force.
When you have that much matter, yeah. Yeah. I'll get to this in a future lecture, but the difference in strength is such that it takes an entire Earth to make a paperclip fall down. But I could get a 5-cent refrigerator magnet and hold it up, and the magnet, this little teeny chip of magnetic material, completely beats the entire Earth. So that's how much more powerful electromagnetism is than gravity, just orders of magnitude at a given distance. So yeah, it takes a lot of stuff, and that's why we don't have nuclear fusion in the core of the Earth or Jupiter.
But if you increase the mass of the Earth, then it would eventually overtake electromagnetic force.
Yeah.
And the paperclip would get sucked.
Right. Yeah, eventually a black hole will beat a refrigerator magnet, or the most powerful magnet we can come up with, absolutely. Yeah, eventually with enough matter, gravity will win. Yeah, it's just, you really have to work hard.
So then if you were trying to lift that paperclip up closer to the sun,
Probably still be okay. You could probably still win, yeah. I think you would only weigh, oh gosh, I think there's a slide to this. So don't quote this number, you watching out there. I think if you went to the photosphere of the sun, you'd weigh 200 times more than you do now.
that's it.
I think that's it, yeah. So 200 times stronger. Boy, I'll look that up on the break, which, my daughter's sending me texts. All right, it's actually a good break time, so we'll get into the solar neutrino problem in just a second. So that's what powers the sun and stars, and we'll pick it up with byproducts of that and go forward after a word from your sponsor. text list. So, all right. So energy from the core, we got that. As I kind of alluded to a moment ago, I didn't look up the question we had. The mass of, okay, I'll have to do it at the end. Your mass on the sun, yeah. All right. We know that from these nuclear reactions, these fusion reactions, another little particle that for a long time we thought was massless, the neutrino, are produced. And there's a very small fraction of neutrinos that will interact with normal matter. And we built big tanks of liquid that would detect the flash of light released by these traveling through. And so we had neutrino telescopes. And what we found pretty quickly was a problem. We always do. Every time you turn on a new observation technique, you find a problem. We only found about a third to half of the predicted number of neutrinos from the sun. So we had a crisis. And you know, there's these moments in your life where you're walking along and you hear something go, I'll never gonna forget where I am. So I was actually in Greenbelt, Maryland at a hotel going to a summer conference with NASA, doing these, they're all-day series of lectures organized by the USRA. And I was listening, I think it was NPR, and they came over and said, and scientists today found out that neutrinos have a very small mass. Like, wow, that's big! I think I yelled in the parking lot. And what we found, the neutrinos do have a very, 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 very tiny mass. And because of that, they can actually change their type and become harder to detect versions in transit from the sun. And so now that we know they have a little bit of mass, they can change type as they go, and that solved that problem. So this is a big neutrino, this is a neutrino telescope deep inside of probably an old mine.
Salt mine in Utah or something?
Probably, yeah.
And a neutrino is a subatomic particle.
Subatomic particle.
Released in a fusion
Yep.
reaction.
Yeah, we get them out of all nuclear reactions. They're just part of the energy mass budget of all that's going on. I believe they were predicted long before they were detected. Like, I think we yes, very true. Yeah, that's one of the reasons we like quantum mechanics so well, is that it made predictions. It made quantifiable, specific predictions that even decades later, but they are. And that is a hallmark of science, which is why some people think string theory, which we'll talk about in the months to come, may not really be science. So.
Okay, so why were they trying to figure out neutrinos?
Because we knew they existed at this point, but we weren't seeing as many coming out of the sun as we should have. Yeah.
It's because we weren't looking at the right mass.
We figured they were massless, and so they should be a fixed mass. So in that case, this number should be coming out per second, and then this fraction of that should be interacting with our fluid in here per second, or per year, or whatever.
They were looking for photons.
Yeah, once it interacts with the nucleus of the liquid, an atom in the liquid here, then it gives off a little flash. You have detectors that are photomultipliers that pick up that tiny little emission of light, and you can tell a lot by what's going on there.
Yeah, I take physics from a guy who was working on this project.
Oh, really?
Way back a long time ago.
Now I think it's IceCube is the latest large-scale neutrino detector, where they're using a polar ice cap, and they've dug channels down into the ice and put photomultipliers down. I think it's a square kilometer, a cubic kilometer of ice that has sensors through it, and they can actually get direction as particles shower through the ice and leave off light. They get a lot of information from the type of particle that came slamming in, and the direction and energy and everything. Yeah.
Just by lowering the temperature by 100 degrees?
No, it's really hard to have a pure, understandable volume of water any other way. So if you did it out in the ocean, you'd have fish coming through, and
Sure, but you got a tank there.
but this is a kilometer cube. So you can't make a tank that big. Yeah. Its size. We have aperture fever even in neutrino astronomy. So. All right, so what hydrogen's used up, that's not the end of the story for a star. It can start to burn helium. And I put quotes on burn because it's not fire burning. This is a neat, I'm going to have my years wrong, but there's a neat observation one can make about fire, as we match fire or campfire fire, that as far as we know, Earth is the only place in the universe, right now, what we know, Earth is the only place in the universe where you can have fire. You need oxygen. And we could only have fire since microorganisms started putting oxygen out as a byproduct. So it's only been a couple billion years that fire even existed in the universe. How's that for? Now, eventually we'll find some oxygen-rich atmosphere someplace else, and that won't be true. But that's kind of a freaky thought that most of the universe there has not been fire, and both in time and space. All right, back to burning. So burning helium to make beryllium. Oh, I gotta check the microphone. I think I did. Yeah, I see it bouncing. And beryllium atom and helium can make carbon. All these larger fusion processes take a greater pressure and a greater temperature to occur. And when you really look at the process and the pathways of lighter to heavier reactants, it can be pretty complex. I mean, it's not as simple as just a high school textbook would actually put it out to be. All the pathways to go. Let's see, I can't even read that. But yeah. It's all about downward gravity and upward pressure from the heat inside. So we have three ways that energy is moved around in our universe. One is conduction, that's contact between layers or between particles. So when I put my hand on the table, ooh, that's kind of cool, I am losing heat through conduction into the table. So that is stuff directly touching. So the atmosphere is warmed by the Earth just in a little teeny skin right on the ground itself through conduction. Radiation is the primary means of much of the inner portion of most stars, and this is by conversion of the motion and the energy in the molecules or the atoms into electromagnetic light, and away it goes in the infrared. That's back to our Wien's law and our Blackbody curve. That's why it was worth going back, because I knew you need that background. And so when I just hold my hand over the table and it starts to feel warm, or the thermometer maybe in the table starts to detect that I'm here, that's a radiative warming. So the atmosphere is warmed by the ground through radiation as well. And the ground gets warmed up by the sun. It takes shortwave light, visible light, and converts it into infrared and is glowing back up. You put your hand on the ground, you feel that it's hot, and that is illuminating the lower atmosphere that's absorbing the infrared. That's the greenhouse effect. We don't want too much greenhouse effect, but we have a lot. The average temperature of the Earth would be right around 32 degrees if it wasn't for the ambient greenhouse effect that already exists from nitrogen, oxygen, water vapor, carbon dioxide, methane, and the constituents of the atmosphere like that. And so the lower atmosphere is warmed through radiation, and inside the star, radiation is the photons making their way through the densely packed material in the star. Convection is what happens in the outer portion of stars. And this is another way our atmosphere also does it. When we get a thunderstorm, you get both conduction and radiative warming of the lower atmosphere, and then maybe some cold air comes in the jet stream. Suddenly you got warm underneath cold, so the warm air rises, and boom, you get a thunderstorm. If you have enough moisture, then the cold air comes down someplace else. And so you see cumulus clouds or thunderstorms, and vertically developed clouds are convective examples. And the outer star works like that too. So when we looked at the sun, we saw all those little cells of bright and dim that were the top of convective columns in the sun's.
Like what's on that picture there on the poster?
Yes, all this little granulation. Yeah. So the really massive stars have a very large fusion engine in the core, and they are radiative all the way up. Gravity has got the material so tightly packed that even though it's not packed tight enough for fusion processes up here, there's no moving. The material is not moving around at all. It's pretty much a solid out to near the surface. For a star like ours, the inner part is densely packed and not moving. You got the fusion core is a lot smaller. Then on top of that, you have convection. You have rising and sinking area. Like I said earlier, very low mass stars are almost entirely convective right down to the core. They're not, gravity is not acting so strongly that stuff is not packed solid until you're right in near the core itself. It's a continuum based on mass again.
And the sizes of these are the weight versus pressure.
Correct, yeah. Now the density of these is a lot lower than this. So if the density were the same, this star would be a lot larger and that star would be a lot larger too. So it's a little deceptive in that way. They are much more dense objects, hence this radiative zone that goes all the way up. So, getting the big picture again. When you have a protostar, stop contracting, it begins to fuse hydrogen, it stabilizes, and it goes on the main sequence curve. Again, based on mass, it can get things going quickly or take a long time for the little stars. It spends 90% of its life in this main sequence stable state, and stars have to have at least 0.08 solar masses to start fusion in their core. Jupiter is, I think, 0.01, a hundredth of the mass of the sun. So you'd have to have some 8 to 20, I think it is, Jupiters to finally turn on. So below us you get brown dwarfs. They are given off the heat of contraction only. Jupiter is a sub-brown dwarf, though it is giving off about 2.5 times more energy than it receives from the sun. It's still cooling from the formation of the solar system. Yeah, we already covered all that in the graph earlier. Low mass stars die a quiet death, high mass stars die violent deaths, and that's where we're going to get into. But this chart is really the whole story of fission and fusion and energy generation using nuclear power in a glance. The difference that you hop between the different elements is the amount of energy released. When you take hydrogen and you make helium, that is the biggest single change in this graph. Helium to lithium takes a little bit back. Lithium to carbon gives you a much less energy. Going from nitrogen to oxygen gives you much less energy. Take uranium and break into lead, it doesn't give you much energy compared to hydrogen to helium. And then you've got this bottom of the graph. This is the important story that iron is endothermic. It's just, it doesn't give it up for anybody. You can break iron apart and you don't get energy out. You can mash iron together, you don't get energy back. So it is the pit of this graph here.
Most stable. The
Most stable, yep. So we can figure out these ages of stars by looking at star clusters. Our assumption is that when the gas cloud collapsed, all the stars formed roughly the same time, given their masses and their turn-on times. And so you plot everything in a star cluster, like H and Chi Persei is the purples. The Pleiades are the kind of greenish ones here. The Hyades, the face of Taurus, the bull, are the dark blues down here. And NGC 188 is this kind of pinkish yellowish here. You plot all the stars, and the bigger monster stars are going to die first and start traveling off the main sequence and up into this initial death zone of stars in the upper right of the chart, where they are more luminous, but their surfaces are a lot cooler because they've expanded. And so they're big giants, red giants up here, and we can just see the cutoff. And we get an idea of what the age of the star clusters are. Once you get enough star clusters, then you can start to pin down what the actual lifespan of stars along the main sequence are. So star clusters and HR diagram helped us figure out how long stars last. So let's get into the exciting death of stars. We've got about 20 minutes or so. So when the hydrogen is nearly gone, helium fills the core, and we call that ash. It's kind of funny. Everything heavier than helium we call metal, and helium we call ash in this case. So we have our own terminology that we bring in as astronomers. And the hydrogen is going to shut off. I mean, it's just not going to give out enough energy to hold it. It's almost like borrowing money from the bank, and then eventually the bank says no more loan. Like, oh no, my checking account's going to collapse. So it starts to contract. When it contracts, you get additional heating from compressing. Anytime you compress something, you get heating. Anytime you expand material, it cools. So you get heat, and pressure goes up, and you start to get helium burning. Now with this increase in pressure, hydrogen can start to fuse outside of where it was before. Remember, this is all radiative, so it's packed in and not moving, but the pressures have shifted, and now you can get a shell of helium burning, a hydrogen burning, fusing around the helium fusing in the core. This is a higher pressure, higher energy, more energy is coming out because you've got this expanded region, so this is going to increase the pressure all the way up so the star gets bigger. Gravity is pulling down the same, but things have shifted here on the subatomic level, and that's impacting the entire size of the star itself. So we're heading towards a red giant phase now. And the star expands, and its surface cools because you have more surface area, but only some additional energy in the core. And so it's energy per area that gives you the heating of that last bit of material in the photosphere. So we see it go from blue to yellow to orange, maybe even red. So Betelgeuse and is it Rigel and, not Rigel, Aldebaran and Arcturus are all reddish, bright, giant stars out there. Oh, I don't know if I want to get into degenerate gas. So I think that's too much detail. You get to the point, helium can fuse, a huge amount of energy is generated in the core, and you get this expansion and contraction, and that process starts. So that's good enough, I don't want to go into that. All right, so let's go down to low and medium mass stars and work our way up to what happens next. So greater than 0.08, solar mass is up to 0.4, so just about half of our sun's mass. These are considered low mass stars. As I showed earlier, they're totally convective. They burn very slowly. They contract very slowly when hydrogen starts to run out, and they just cool down to small, hot embers we call white dwarfs. They're hot because even though you're getting less and less energy out of it, their surface area shrinks down tremendously once hydrogen shuts off. And so you have less energy coming out, but a tremendously smaller surface area of the star. So we see them heat up to the blue region of the spectrum and Wien's law. And so they become white hot, but just very small. And then over very long periods of time, they radiatively cool down and become just cinders in the very, very, very distant future. The universe has not been around long enough for white dwarfs to significantly cool. So the universe is too young to have red-colored white dwarfs at this point. Medium mass stars are about half of our sun's mass, up to 4 times our sun's mass. They can go from hydrogen to helium, but they're not large enough to then move on to carbon. These do become red giants. They swell up. They don't mix well, so you don't get new hydrogen down into the core. So this swelling actually starts to puff off the outer atmosphere of the star into space, reducing the mass of the star, and that shell of material that heads out and drifts away on solar pressure, solar energy pressure, creates a planetary nebula. They puff off enough, eventually you have a white dwarf ember left over, just like the lower mass stars, and then they're going to cool off for a very long time. They do need to shove off enough mass to get below 1.4 solar masses, and we'll see that. It's called the Chandrasekhar limit, and we'll get to what that is in just a moment. But this is the Ring Nebula. There's a little white dwarf in the center, and here's a big shell of puffed off material. Again, this is really small, but it's really hot. It's giving off a lot of ultraviolet light. So this is an emission nebula. It's pumping up the hydrogen and the helium that's been puffed off into space, and some dust, but mostly hydrogen and helium, and is making it glow. And planetary nebulae were called that because they were ghostly little objects that roughly looked like distant planets. They had a disc-like shape to them until telescopes got better. And so that name sticks. We never throw anything away. Astronomers are hoarders for names and conventions. And they depending on the rotation of the original star, we believe the magnetic field of the progenitor star, they can have a wide variety of shapes. Also the angle that we happen to be observing the system from. So where its rotational axis was compared to us Earth observers looking at these things, you get a wide variety of beautiful things. So the Hourglass Nebula, Cat's Eye, here's the Egg Nebula, wild, pretty stuff. All right, white dwarfs can create some other interesting phenomena in the universe. If they were in a binary star system with, say, a partner that was lower mass, then they would have gone through their life and done their business, been now heading into white dwarf category. And the next star then starts to enter the swelling red giant phase of its life, and you can get their part of this new swollen star past the gravitational tipping point of the system. They're going to rotate or revolve around each other around the balance point between them based on mass. And so once that tipping point is between beneath the surface of the swelling star, some of the material is just going to start falling down onto the white dwarf. The tipping point of the Earth-Moon system is below the crust of the Earth. So if the Moon had a strong enough gravitational force and the Earth was more gassy, then we would lose part of the Earth falling that way. And that material can build up in a disk, an accretion disk, around the white dwarf to where densities in the center reach the point where nuclear fusion can occur. But it's not in the middle of a star, it's on the surface of an object. So all the energy instantly blasts out into space, and you get a nova. This is not to be confused with a supernova, this is a nova. And they're bright, but they happen at a certain buildup of mass where density reaches that, and that's pretty reliable. So we can look at the light curve of these things and we can figure out some of the physics of what's going on between these two and like that. If the system is stable, you got this constant source of the same amount of stuff coming all the time and the buildup rate's the same, nova can reoccur. They can build up and blast, build up and blast, build up and blast. And we do see reoccurring nova out there in the universe. What is going to happen to Earth when our sun does this? Because our sun is between 0.4 and 4 solar masses. And we are right about here at the 5.5 billion mark in the sun. Our sun contracted as a protostar, began its main sequence life, and it's slowly warming. So global warming aside, from anthropogenic gas buildup here, the sun itself is warming. Very slowly, but it is warming over time. And that is one of the paradoxes we have is when we do long-term climate modeling, is we look back and say, why wasn't the Earth just covered in ice all the time way back? Because when you ran some of the earlier computer models, long-range models, an ice ball Earth occurs a lot. Once your model falls into the ice ball, it just doesn't go. Reflectivity of the Earth is near 90%. It's very cold. The sun is not really warm back then, and it never melts again. So obviously that didn't happen. We've had giant ice ages, but we've come out of all the ice ages. So that's been always kind of fun to figure out and work with in climatology. But in the future, it's going to keep warming up until the point that it leaves the main sequence. Then the contraction starts happening, more and more energy comes out, then we have the conversion to helium burning, and then the sun settles down a little bit. We have a much shorter period of helium core burning, because there's not as much helium as there was hydrogen, and it's also not as much of an energy source. And so then it tries and can't burn the next material, and we go into the puffing phase of sending out a large amount of the mass of the sun into a planetary nebula, then it cools off, heading towards a white dwarf in the future. So there's our future. Depending on, the mass loss of the sun will mean that the Earth's orbit expands, but the encroachment of material from the sun out into the solar system will definitely swallow Mercury and Venus. There may be enough friction on the Earth to cause its orbit to decay. And I hear papers go back and forth as to whether we're going to spiral in and get consumed in the sun in the end, or whether we drift out, get roasted horribly. I mean, you get this giant bloated 2,000 degree red dwarf, red giant sun looming in the sky, boiling off the Earth's oceans, atmosphere is gone, rocks melt, and we have just a magma planet, kind of like a Mustafar in Star Wars, hotter than Mustafar. But we don't know. And also, NASA's actually done the math of what it would take to bring asteroids in and lock an orbit outside of the Earth's orbit. So every time the two bodies pass, the Earth gets a little tug outward, and over 10,000 years or so, we could tug the Earth out to a definitely safe distance to preserve it from the hot, fiery end. But then eventually the sun isn't going to make the energy we need to keep everything happy here. So now the pyramids are only 4,000 years, 4,500, 5,000 years old. So we'd have to have an engineering project to save the Earth from this that doubles the life of the pyramids. So that means every funding source from all the governments have to stay stable for 10,000 years. Oh yeah. All right, then on to massive stars. This is where the fun happens. Massive stars can pass carbon and get to the carbon detonation phase. They go from oxygen, neon, magnesium, sulfur, then silicon. The hydrogen phase may last 7 million years, helium 500,000, carbon 600 years, oxygen about 6 months, silicon burning for about a day, and then we get to iron. And when it tries to make iron, the rug gets pulled out from inside the star, and the fun happens. So there we are. The star tries to make iron desperately. I'm anthropomorphizing here, but tries to make iron, and there's not going to be any energy released there. So it's endothermic. The core, as far as the star is concerned, cools suddenly. The pressure just vanishes, and the core collapses in less than 1/10 of a second. And depending on the mass, you either get a neutron star or a black hole made. The upper part of the star falls, encounters this incredibly dense object in the process of either neutron starring or black holing, and bounces off and explodes out, rebounds out into the universe, and you get a supernova. This is the big show here. The core and this rebound produces more energy than the entire visible universe, visible galaxy, gosh, and goes out in the universe in just a few seconds. You got a tremendous blast of neutrinos from these that actually impart momentum outward to material that's being ejected. These neutrinos are so ghostly that we can hardly detect a few, and giant takes or cubes of ice are now actually pushing matter around, and it's just unbelievable, the energies and violence going on here. The remains can expand at well over 1,000 kilometers a second. Famous supernova in history, we got the 1054 blast that's now given us the Crab Nebula in Taurus. It peaked at -6 magnitude, so it was approaching the brightness of the moon. 1572 AD, Tycho supernova, -4. 1604, Kepler observed one at -2.5. Might have had one in 1667, Cassiopeia A, formed by, but we can't find anybody who made actual observations and recorded that one. No estimations of how bright it was. And then most recently, supernova 1987A in the Large Magellanic Cloud got to 3rd magnitude, but that's not in our galaxy. That's in a satellite galaxy of our galaxy, and it got to be an easy naked eye object. That's a lot of energy being released.
So are they supernovas made of iron? Or is it iron that makes up a supernova? Because it never gets there.
It never gets, yeah. Iron and some heavier materials are made during the blast moment. During that rebound and explosion, outward densities go really high. But as we'll see in the neutron star section here, a lot of that heavier stuff is made by neutron star mergers, which we just recently observed and figured out. But we're waiting for another. We've had quite a drought here. We've had in, 1,000 years, 5, so that should be one every couple hundred years.
We just had one now, 1987, right?
Yeah, but that wasn't in our galaxy. So these are all in our galaxy. So we haven't had one since the 1600s in our galaxy. Yeah. So come on. Bring it. I want to see a supernova in my lifetime. And you can catch them in other galaxies, and that's, we have many observation techniques and programs observing supernova, because as we'll see, they're helping us figure out the large-scale geometry of the universe and what's happening with dark energy and stuff like that. So, you know, if you don't want to wait 200 years, don't just stare at one galaxy. Look at 200 galaxies, look at 1,000,000 galaxies, and watch them all for the stars going off in them. So there's the Crab Nebula, stellar remains. We have a lab that we worked on even back in the 80s. We had, at Arizona State, we'd run a lab for cloudy nights with a picture taken a couple hundred years back and a picture more recent. And the students used the star field as a baseline and would measure you just would pick globs of material here, measure it and out from the center, and they could calculate the expansion rate of the material. So in pictures that we've taken, we can still see the material expanding outward. So if we didn't know that this was definitely caused by a certain supernova, you can just run the expansion rate backward and see when it was all in one point. So the blast is still blasting. There's Tycho Supernova Nebula. That's a weird looking thing. I'm sure it's a Hubble. Looks like something you'd see in the produce department.
Looks like top of somebody's head.
Yeah, it does kind of look. Here's Kepler Supernova Stellar Remains. All very recent. Cassiopeia A. And supernova 1987A, we see a ring of compression and heating going on, spreading outward, and it seems to encounter other nodules and density of stuff maybe ejected over time into the interstellar medium before, and now this shock wave is overtaking that, and we see these little hot spots that change.
Are those potentially new systems forming?
I don't think so, not on this scale. Yeah, I think we're still smaller than that. And so here's where the stuff is made. If we look at what we know about nuclear fusion rates, these are the efficiencies of material created. And except for the upper end, which we now have neutron stars to thank, the lower end was well explained by this progression of material creation inside of stars, and then accounting for what percentage will probably get spewed out into the interstellar medium.
So the atomic number increases with each
Correct.
change.
Yeah, and so you get fewer as you go. Yeah.
And this is working towards the black hole, I think you alluded to that earlier.
We'll get to that. Yeah, we're going to get to neutron stars, and maybe not this time. Maybe I'll have to come back next time for black holes. So, talking about the neutron stars and the heavier materials here, this is just the little news briefing, little astro update from a few months ago, where we have the gravity wave detectors, the fourth signal to date, which there was actually another one that was questionable. I think they may have decided that the questionable one that I talked about in yet another astro update was a real signal. So I think they're counting this as the fifth gravitational wave signal. 2 seconds later, the Fermi Gamma Ray Space Telescope caught a flash in that direction of space lasting under 2 seconds. So we had a gamma ray burst that coincided with this gravity wave event. And other telescopes jumped in, and this is what the signal looks like in the data. And what they figured out was that this is a merger of two neutron stars in another galaxy. NGC 4993, 130 million light years away. There's the optical blast from the two coming together. It's a Hubble image. And as the neutrons came together, so the problem with the supernova blast is that just not enough neutrons were there to pump up all these really heavier elements and create them. You can't have 92 protons together and have a stable nucleus for uranium. You have to have that many neutrons too. And it just had, it was one of those little secrets that astronomers are not comfortable about, but this does it. I mean, you've got 2 neutron stars merging, you got plenty of nucleic material for gold, platinum, uranium, neodymium, or whatever. So that does solve this. The heavy elements pouring out have the neutrons needed in this merger to do it. We've been able to directly see the spectra of these heavier elements in the cloud expanding out from this object. So, ta-da, I mean, we've got the smoking gun, we've got the gun, we've got a written confession of what's going on here. The remnant was 2.6 times as massive as our sun. Did it turn into a black hole or a hypermassive neutron star? We weren't sure because we haven't seen a neutron star at this mass. It faded out quickly, and so this gives us the Big Bang giving us hydrogen, helium, and lithium, mostly. Stellar furnaces give us lithium, iron, a little bit more. And then neutron star mergers give them maybe as low as calcium all the way up to iron and uranium and anything, all the other short-lived radioactive things. So one neutron star merger about every 10,000 years in the Milky Way, but we look at enough galaxies, we're going to see enough of these mergers. And with the gravity wave detectors getting the first whisper, and we're making those, I think we're still building one and finalizing one and we're making them more and more precise, more and more sensitive. We're going to get a lot more data very soon looking at these things. Another thing that this answered, one of the questions, we'll get to what dark energy is and dark matter, but one of the problems with dark matter is that people say, well, maybe the speed of light isn't a constant. And that maybe you get that to help solve the dark matter question. But here we have gravity waves. So gravity waves are completely independent of electromagnetism. And the light coming from this event, and after 130 million years of travel time, the difference is only a couple seconds, which can be explained by how long it took the light to punch through the shell of opaque material around the event. So we know that the speed of light is constant to within 1.5 quadrillion. So I think speed of light is pretty constant. We're pretty happy with that now. I'm trying to remember here. Oh, did that not make it? Oh, good, yeah, okay. So we're going to go now into is the update for next month. And actually, we're at noon. Do you want me to go a little further, or do you want me have you had your fill of neutron stars for now?
So a neutron star is formed by a supermassive sun that collapses.
Yes. A core collapse, yeah.
And then when two neutron stars collide,
Right.
it shoots off material heavier than iron.
Correct.
So the gold in my ring or the neodymium in my
Cell phone.
or whatever, which all came from the sun.
Double neutron star.
Double neutron star. The dust cloud congealed onto the Earth.
You got it. And Carl Sagan had it right. And he said, you and I, we were made of star stuff.
So that's kind of my question. Is there a timeline that explains all the really heavy
Well,
elements we have here?
look at the giant stars. The giant stars only last 10 million years. In a universe that's 13.8 billion years, you have lots of generations of the giant stars.
And it
They could be
doesn't mean
spewing
the
stuff.
sun exploded
No, no.
It's
Yeah, our son's probably second to third generation, depending on what all happened and how stuff mixed in the gas cloud that eventually formed our star cluster.
so like about every 10,000 years, there's some neutron star collision.
In a given galaxy of our size, yeah.
And so are we collecting material from the other side of our galaxy?
No. Yeah, it'd be in this neighborhood. Yeah. There is work to identify the star cluster that our sun formed in. I think there's been some effort, success in figuring that out. They've got a handful of stars that are now pretty far spread out around our arm of the galaxy that were born with our star. So our sibling stars are a hunt that some astronomers have taken up. But our star cluster 5 billion years ago is not only has it dispersed all the gas and dust in it, they've all drifted apart. So just like any family, they grew up and moved away.
So Mars should have the same relative amounts of
certain isotopes and things. Mm-hmm. Mm-hmm. Yeah, there's a certain atomic signature to the materials in our solar system. Yeah, similar to the sun.
The only reason we exist as we do is because of gravitational pull and keeping those things in,
Mm-hmm.
and then evolution of everything. But
Yeah, I'm reading a book called Complexity and the Arrow of Time, and it is blowing my mind so much that I'm going to only take a couple pages at a time. But one of the big ideas is that gravity is a temporary anti-entropy force. So it pulls back locally on disorder and like that, creating order. I mean, you've got differentiation of the core of our planet, we've got atmosphere on top of ocean on top of land, and you've got all the physics going on inside of stars. But all this was pretty homogeneous mixtures of stuff that was pretty high entropy. So you've gone from a gas cloud down to all this coherence and computers and technology and like that, all from gravity.
so the only way to repeat this if we go to Mars is to create our own atmosphere.
Yeah, we would have to, yeah. We're very fragile.
Nothing else
Yeah.
has it.
But it's temporary, and at the expense of creating more entropy outside of where gravity's acting. And that's what all this light coming out of stars is removing energy and information away and scattering it. It's
And gravity be destroyed by, emissions and things like that. I mean, that's not
no,
the same realm.
yeah, no, gravity it's the curvature of space and time caused by matter. And where you have matter, you have thermodynamic processes, because you have heat being transferred. Where you have heat being transferred, any thermodynamic process, like I said, my information and Are You Living a Simulation talk, that where you have thermodynamic processes, you have an arrow of time. So time marches forward because thermodynamics is occurring. So it's mind-blowing. we just love neutron stars in the dust.
Okay, so I've got a big explosion throwing material out into space. And materials eventually start collecting again. And the materials, because we have big veins and big pockets of stuff here on Earth.
Mm-hmm.
So these particles aren't necessarily small, tiny particles floating around in space. They collect to be a big, giant chunk of fluid, let's say.
Yeah.
Right? And then when it collects on Earth with plate tectonics and whatnot, things move and shift, and that creates the veins, maybe, or
Okay, but you also have
because we're not creating gold.
no, but you have in a magma pool, you're going to get a differentiation based on density. So we have melted rock and material. Heavy stuff will sink to the bottom, light stuff at the top. Then depending on how the eruption occurs, you're going to have things just flow out and get deposited or just cool and ground in different areas.
Change.
Right. Chemical processes are temperature based, yeah. Yeah.
Didn't I say that the gravitational wave from those two neutron stars colliding, they determined that it produced enough gold for like 10 Earth masses?
Yep.
That's quite a bit.
That is a lot.
Quite a bit of gold.
Yeah.
Unfortunately, it's spread out all over.
Right.
Area of the galaxy that it happens in.
Yeah. Well, most of the core of the Earth is iron nickel, with all the other heavier stuff. So there's uranium and thorium and cesium, plutonium, things like that are down there too, because they're the heavier stuff. And some of the heat of the interior of the Earth is nuclear breakdown. So you have nuclear fission occurring in pockets and in areas deep inside the Earth. And just uranium atoms sitting alone will break down eventually. It is naturally radioactive. It doesn't even need to have a fission reaction occurring. It just will eventually do it randomly. Yeah. So eventually that will run down, as will the heat of the formation of the Earth will run out as well, and the Earth will start to solidify. I think that plate tectonics is expected to turn off in about 1.5 billion years, which is pretty soon, yeah. And at that point, the processes that are forming the continents and like that shut off. So weathering is going to take over pretty quickly. I mean, on a geologic timescale, mountains are sugar cubes in the rain. They'll just go down, and we'll have a water world with mud underneath it. And that will be how the Earth goes into the end with the sun. So, yeah. There's a cheery thought for your Saturday.
Do astronauts age less quickly when they're in anti-gravity?
Say again?
Do astronauts age less quickly when they're in anti-gravity?
Well, you mean in free fall? Because I mean at the microgravity, at the height of the International Space Station, gravity is at 90% of Earth's surface strength. At the moon's distance, it's at 50% of sea level strength. So there's still a lot of gravity, but they're just falling. I don't think you can say they age. I mean, they actually would age slightly faster based on general relativity, because they're outside of gravity. Gravity slows time slightly. Black hole slows it ultimately. We'll get to that next time. But there's an awful lot of physiological things that are really rough on the body without gravity. We are made to have gravity pulling down on us. And I would guess that more harm is done being in zero gravity, microgravity, than would be benefited by not having gravity. So.
The twins, one of the twins that just went up and was actually taller.
Right.
And I guess will remain taller?
Yeah, I think DNA, yeah, you have gene expression. The DNA itself doesn't change, but basically the software that's reading the DNA and what parts of the DNA it's reading from alter. I think it's epigenetics, is that? And that altered, probably permanently, I think, yeah.
Did they mention age between the two?
Well, it would have been only microseconds in general relativity-wise. It would. I don't know. All right. Well, we'll pick up in the middle of neutron stars next time. Thank you all.